Hello, everyone. Welcome to Connections for Life Live. I'm one of the hosts, Ted P.
I'm Chad Kuva.
Joe Surratt. How is everyone?
Okay.
I'm the victim.
Victim of the month
There he is.
is Mr. Dirk Smith, the one and only living legend from Ionix. Here
And I'm
today.
Lando and Jack, the living legend from in the natural gas industry, right before the 4th of July holiday. It doesn't get any better than this.
Yeah, well, we're excited to have you on. I think, we did a similar presentation during the Upsco Expo, and I thought it was phenomenal. It really did a deep dive into static electricity. So we have you here for that, and we want to just say thank you for taking your time to be with us.
Absolutely. Well, you remember, it may be static electricity to you, but it's bread and butter to me, so I'm glad.
Oh, there he goes.
That's how we're starting, Dirk.
Well, I've got to get some new writers, and I just
send it out on Fiverr.
So here we are. So Dirk, like I just said, we're going to go through. We're going to just quickly go through some the intimate details, if I can get my computer to work, of static electricity. So I'll let you get started with the very first slide. Just what is static electricity?
Well, what happens is a lot of times when I do presentation and when people ask me questions later, they still don't really understand this. This is the most fundamental thing you got to understand about static electricity is it's still electricity. The only reason it's a problem for the gas industry, it's an electrical charge that's sitting on a material that is not an electrical conductor. It's sitting on polyethylene. And so what happens is if you don't get that concept that electricity is just immobile, it's static, it can't move on that material, everything else about static electricity is not going to make sense. I have people say, hey, I'll go through the presentation. They say, okay, if I wrap some wire around the end of it, will that conduct it away? They still haven't gotten the fundamental concept. If you get the concept that it's electricity that's sitting on a material that won't let it move, you're 3/4 of the way to understanding what's going on in your system, what static electricity is doing in it.
Sure. And so I guess that brings us to the next question. How is it created? How does it end up there in the first place?
Yeah, a lot of times in physics, it can be done a lot of different ways. But in the case of the gas distribution industry, it's friction. It's the friction of two electrical insulators rubbing against each other. Now, that can be, in our case, it's methane rubbing against polyethylene. But it also, and I'll talk about this a little later, it can also be that methane rubbing against a coating on inside a metal pipe, and that coating is electrical insulator. Charges can build up in metal pipe too, but it's the friction of the passing gas. It mechanically shears off electrons, and these electrons just accumulate in random places, and we don't understand why they do it in particular places, but they do, and they build up, and that's your problem.
So there's literally no science that tells you why they go to a certain spot on
No.
That's crazy to think about.
Yeah, it is, because it's a real problem. Because here, the problem is Mother Nature is designed to be at electrical neutrality. And so what happens is, in a gas system, up in nature, what happens in a hot summer, like you guys are having a hot summer up there in New York, the static builds up in the clouds and it arcs to ground and gets rid of dissipates the electrical imbalance. Well, problem is in your gas system, if Mother Nature decides to do that and you happen to have a guy in an excavation with repairing it, it can be pretty messy. So that's the reason you need to control it. Or otherwise, it's going to act out on its own, and you can have a real mess on your hands.
Well, that brings us to the next slide that we have in the presentation, the 4 basics of static electricity and polyethylene pipe. I know that this is something that I want to spend some time on because I think it really details kind of just the rudimentary understanding of where it is, how it develops, and kind of gets us a baseline of that. So if we want to just move on through those slides, number 1 here we go.
Yeah, this is the most fundamental thing. This is the root cause of every static issue you have. Now, I'm going to show you a little later. Static causes 4 problems. It causes ignition, it causes shocks, it puts pinholes in pipe, and it also burns out your solid state electronics. But every one of these problems can be traced back to a root cause that the static starts inside the pipe by the passage of gas. It's that friction of your compressors pushing the compressed gas, rubbing it against that inside wall of the polyethylene pipe. It shears the electrons. These electrons accumulate in random places inside that pipe. And when they have the opportunity, they'll cause those 4 problems. This is the root cause right here. It'll always be traced back to this. I'll tell you a story about later at the very end about a locating transmitter was all burned up, and it came about from static inside the pipe. The locating transmitter was a quarter mile away, and it got burned up. That's always the root cause. So what happens is, this is what GRI research has done. The LDCs, gas companies have paid for research, and this is just a citation, confirming what they found in this.
Moving on. So number 2.
Well, what happens is, remember, static electricity is called a static electricity because the electrons are in a material that's not electrically conductive. If I put those electrons on a piece of bare copper wire, they'd move. But when I put them on a piece of polyethylene and I put those charges against there on that surface, they can't move. They just sit there. They're frozen. And so once it's created, it's just not going to go away. You can't wish it away and say, oh, well, it's, I haven't had a problem, or it's not there, or it'll go away on its own.
Unlike warts, huh?
Well, another story. We'll save that.
Different story, different time.
Different time.
Here's
So here's where GRI said, that they proved it. They said they confirmed that once you get a static charge generated, it stays on the surface because the polyethylene doesn't conduct electricity. It just stays there.
Well, number 3, obviously, we have a lot of procedures for the static on the outside of the pipe, but you want to just talk about that?
And this is something that is not intuitively obvious. Most people do not realize. I told you how it's created. Well, if it's created on the inside of the pipe, why in the world are we worrying about something on the outside of the pipe? And the reason is you can explain the physics, but it really isn't necessary. It's been proven by GRI that what happens is that when you create a static charge on the inside of a pipe, it creates a charge on the outside of the pipe. And so you've got basically, when you're working on any poly pipe in gas operations, you got to remember you got 2 charges to deal with. One on the inside of the pipe, one on the outside of the pipe.
And then number 4, arc.
Mother Nature is going to arc the ground. It's, it wants to go to electrical neutrality. So either you control it or it's going to do it on its own.
Another citation.
And again, another citation from GRI, where they just show that that's the case.
So the 4 basic threats, you kind of just touched on that, but let's just go through those because I think that that's a really pivotal specifically for our industry.
Yeah. The industry is everybody's pretty well understands that ignition causes the static causes an ignition, which is a personal property threat. But there's a lot and there's fatalities because of ignition, sadly enough. Shocks, there have been close to fatalities, but not fatalities. But it's much more common than people realize of workers getting shocked from the static generated inside the pipe. The third thing is on electrostatic leaks, and I just, people need to recognize that it's more complicated than what we can get into at this time. But I've seen distributors fight pinhole leaks for years, replacing pipe and think it's a problem. And it's caused, and gas research says it, and plus a lot of independent labs, forensic tests of pinhole pipe, it's caused by static. And then finally, what's happening, the industry is getting away from mechanical metering devices and SCADA devices to solid state. Those things are used, like your phone here, that's used to being on like 1 to 2 volts. You start getting some of these pipes where if you've got a pinhole leak in the service line, the voltage was like 45,000 volts.
Wow.
Oh yeah, serious voltage. No amperage, but a lot of voltage.
Wow.
But if that, all it takes is just a little bit of that 45,000 to arc over an isolation joint to a service meter, and it's gone.
Poof. Right. Yeah. Well, let's dig into the ignitions ignition source of leaking gas. Let's kind of just talk about that a little bit.
Yeah. Essentially, what happened? It's odd because there hasn't been a real understanding of static electricity in the industry. What happened is guys would, they kind of said, well, we had an ignition that was a rock falling down and caused a spark or something. And GRI said, no. What's happening is by just in the normal operation of pushing gas through a poly pipe, you get friction. It builds up static electricity inside that pipe. So if you have an ignition, then you can't account for an ignition source. It de facto must be static electricity. There's no other that is the most reasonable explanation, simply because in the absence of a known ignition source, that methane being pushed through a line is creating static inside that line. And so that's how it starts, and that's why you need to address this problem and be aware that is going to be your primary ignition source of any ignition you have in poly pipe and metal pipe.
I really like the next slide because it's funny because you see the perfect quote here. It creates its own ignition source. Like it's really what it does. I mean, it's a unique problem for gas distribution because you are having an issue where you don't want to have an ignition source, but you're actually creating one by piping the product through the pipe.
And poly is terrific. What a terrific material. This is the one issue. If you deal with this issue, you literally have a 100-year life product that is basically perfect. So you got to deal with this. And so whenever you have the three conditions, if you have an interior pipe surface exposed, you have a gaseous mixture and proximity to electrical ground where that charge can neutralize itself, that's where you've got to see that as a potential static ignition risk in your operations. So
that brings us to
in talking to people, remember that there's always going to be, remember the beginnings, GRI says there's a static charge in the inside, static charge in the outside. So most operators have only been used to dealing with a charge on the outside of the pipe, but there is one on the inside. So what I did is in these next slides, I just kind of categorize, I go through them to understand where the static is. For instance, like, and it's very standard third-party damage. Where somebody digs in, what happens is the static, when that pipe gets broken, or when you cut into it, let's say and for some reason it's blowing gas, or it's broken, or some reason it's blowing gas, the static is caused by friction. Well, the friction gets a lot worse. If you've got a broken edge on that pipe, there's turbulence around there, and that turbulence creates friction, increased friction. That increased friction creates static electricity. The charge is like on the inside edges, right where the break is. So when you have that operation, you're looking to get your guys to get rid of that charge in that little where the static is, where it's like inside the cut, inside the break there. It is on the outside, but it's also in the inside as the gas is uncontrollably coming out, and there's a lot of friction. So that can be third party of that. And it's purging is the same way. I mean, purging is, basically, controlled third party damage. Really. Sure. So what happens is you've got to be careful that static is on the inside edges where I've got it in red there. Now and we're going to I'll talk a little bit about this a little later, but on this illustration, a lot of people use a grounded metal purge pipe and they think that's completely safe. Well, it's not, simply because unless the pipe is perfectly clean, you can have patches, coatings or grease or something where static can build up. So you think that's all getting grounded when in reality that passing gas going through the pipe has created friction. With the static charge building up on a piece of grease in there, you're looking at the grounded pipe and say, oh, everything's okay. No, it's not. So you want to be sure to get rid of the static inside that pipe before you get near it.
Wow. And then in the next one that's a little bit more near and dear to our hearts.
Oh, yeah. And this is something that the static squeeze off causes both a static ignition risk and a shock risk. And I'll talk more about the shock risk and what you need to do about it. But the highest static charges you're ever going to encounter in gas operations are during squeeze off. I mean, really huge things. And so what we recommend is you spray off the surfaces before you get near it, because remember, it's caused by friction. And when you start to squeeze that pipe down, the velocity picks up, and man, the static charges downstream get huge. So you need to, usually we recommend spray it off before you start squeeze off, then spray it again before you start working on it, and then spray into it with a reach tool. Don't get near that until you've got that static under control. Hundreds of thousands of volts.
I didn't mean to jump slides on you. My mouse got stuck, so I was like, I apologize. But moving on.
Way to make it shorter, Joe.
Yeah, I'm just flying through.
There you go.
Come on, Dirk, let's get this over with.
Okay, I'm going to take the guy in the FedEx. Hot taps are another thing. Our topical aerostat is perfect for hot taps because you're drilling in and the static is inside the pipe. And I remember one time getting a photo from an operator, and they're trying to get rid of static by using a grounding strap inside this threaded tapping tool, and it's chewing up oh my gosh, what a mess. With a topical anti-stat like ours, you just spray it in the fixture and you're done. But your static is where your tool's going through into the pipe. and it could. And when since you're pulling it out, then you have the opportunity for a static ignition. So you got to be careful in that operation. And finally,
Cutting.
When you cut into a pipe that's been under service and you hit into static, one of the saddest incidents happened out in West Texas about 5 years ago. Standard O&M operation, and it caught fire with his kid in it, and he was in a burn unit intensive care unit for 2 months.
Wow.
2 nurses round the clock, and it was just cutting into a piece of pipe. The static, he hit a static and it ignited. And so whenever you're cutting into a piece of poly pipe that's under pressure or it's coming out of pressure, you want to try to get rid of the static in the cut near that before you get near it. It's not perfect, but it'll work.
Go ahead.
I've what may be a stupid question, probably is. I usually come up with those. When you're squeezing, if you never actually, I know you're building up that static in there, but if you never cut the line, say you squeezed and you never cut the line down the line farther, say you just squeezed it off, did your maintenance somewhere else. I know you built up the static, but without like oxygen getting into the pipeline, does that static, does it never disperse after that? You know what I mean? Like I guess that's my question is, I know that causes the ignition, but with the natural gas, would you have to have oxygen from the air to ignite that? I guess is my question.
Well, what happens is it's very rare for gas to burn back into a pipe. It's happened occasionally. I heard an instance in Georgia where they'd shut off the gas flow and a fire got started and it went back up into the pipe. That's unusual. It's just that downstream from squeeze off, and there's been no research downstream of how far the static goes during squeeze off. But if it's far enough downstream, if you cut into that, you're now having your tool as a grounding source. You've got, at that point, you got a gaseous mixture, and the static charge is sufficient that it will arc to a tool, to the person, to the ground.
That answers my question. That makes sense. Thank you.
So we kind of touched on plastic pipe, but I know there's also static in metal pipe.
That is a real bug. Everybody thinks that there's no static in metal pipe. You have a picture of the next slide?
No.
Can you move the next? Does there a pipe?
No, I can't talk about this one now.
Talk about this one.
Yeah. This is a slide of a Tennessee gas pipeline in Hanoverton, Ohio. Probably, Ted, right in your backyard.
Jack.
And this was a farm. This was a farm. Clear night, no weather, calm skies, and the Tennessee gas pipeline failed. Well, they'll do forensics. They'll be able to do failure analysis and say what the cause was, bad well, whatever. But the point being is, why did it catch on fire? What's the ignition source? This is in the country in the middle of the night. Nobody there. What's the ignition source? I wrote an article about 15, 20 years ago. It was published in Pipeline and Gas Journal. And I took all the National Transportation Safety pipeline incidents that rose to their level of investigation. There's far more hazardous liquid pipeline failures than natural gas. But in hazardous fuels like kerosene, gasoline, crude oil, diesel, if they fail, there's virtually a zero chance they'll ignite. There was one instance 20 years ago in Washington State where a pipeline dumped 1 million gallons of gasoline and it never caught on fire.
Wow.
On the opposite side, in the NTSB, if you go look at them, if it's a natural gas pipeline break, virtually 100% of the time it'll ignite. What's the difference? They're both hazardous fuels. It's the static electricity. When that pipe broke, it's got coatings. It's got areas where there's isolation, electrical isolation. The friction builds up on those areas. It arcs. It gets higher and higher, arcs the ground. And once that first methane molecule is ignited.
What's amazing to me, Dirk, is that most of the time when they do internal linings, it's because they're trying to reduce the friction in the line to make things move faster. I mean,
But I have a question. And this may be a dumb question. It probably 100% is. But like gas, oil, diesel, because they're liquid, do they not have static in the?
They don't create friction. Yeah, there's no friction in it. No, there's no friction.
Wild.
But a gas does. A gas does. But a liquid doesn't. And so, I mean, it's smart. I mean, it's not kind of, sometimes in statistical studies, it's like 60-40. Oh no, it's like 99-0. You have virtually no hazardous liquid pipelines ever ignite. And because if you go to people right now, I do this when I do a class. I say, okay, what do you think? what has more pipeline failures, hazardous liquids or natural gas? They always say natural gas. And
because those are the ones you hear about.
Yeah, that's the only ones you hear about. That's because they ignite. There are far more hazardous fluids, hazardous liquid pipeline failures than natural gas, but they never catch on fire.
They don't make the news. Wow. I just want to point out for everybody that may or may not be watching this, I guess I didn't really digest this picture initially. Do you guys notice how high those flames are? Like in compared to the silo.
There's a little silo. There's a 50-foot silo to the left there.
Right. That's incredible. What size line was this? Do you know?
Well, it was probably a 36.
Had to be 36 or 42, something like that.
Yeah.
That's naughty. Anyways, all right, moving on.
Yeah, moving on.
Shock to workers.
Shock to workers. And primarily this is going to come back, we'll go to squeeze off again. And what happens is, remember that because of the Venturi effect, the velocity of the gas picks up, the static builds up inside the pipe, primarily downstream, but it's also upstream a little bit too. So what happens is, when you're doing squeeze off, you got to be really careful to keep guys away from that until you've neutralized that charge on the outside. So, if you got I think the next slide there, if your mouse has decided to come back to work, your mouse, one more.
No, I don't want to go one more. You said one more, and I want one more. Now, I should just let you control it. Hold on. Here.
Yeah. So, So you want to make sure. Here you go. So you just want to make sure whenever you have a squeeze off, you really got to make sure that guys dissipate static before they get close to it, because, like I said, the charges will get in a couple of 100,000 volt range. Now, I think one of the next slides it talks about, I show there's again how it is. The Venturi effect causes this buildup downstream. So when you're downstream, when this guy's down there near that squeeze off, if he's not using a grounding strap, what happens if that charge gets big enough, it can arc through the wall of the pipe, go through the tool, and if he doesn't have a grounding strap, the worker becomes a grounding strap. And Steve Jocelyn in Connecticut was telling me they had a incident in the Northeast about 4 or 5 years ago. I've never had a fatality. Very common when I teach this class. Very common. Somebody comes up to me afterwards and said, "Yeah, I got shocked. I got knocked out of the excavation when I was a field worker, back a long time ago." But it was one guy where they had to resuscitate him. His heart stopped. The shock stopped his heart. They had also amputated his toe. One of his big toes, because of the static charge going through them. And it's really important. I hear stories about field guys removing the grounding straps from their squeeze off tool. Don't insist these guys do.
I've seen that on more than one occasion. I wanted to apologize to everybody that I just picked up my cell phone because I had to yell at my kids via text who were bouncing around upstairs. So I didn't want to be rude.
I didn't even notice.
I didn't even hear it.
I was paying attention to Dirk.
I felt bad because I try not to touch that thing. And I'm
Dirk, what were you talking about again?
Yeah. I was talking about
this whole thing over since Joe ruined it.
Upstairs.
So let's talk about why we ground the tool. You just kind of touched on that. Yeah, I've seen it on more than one occasion. Squeeze off tools come with grounding spikes or different methodology, and I've seen them been taken off because they've been a pain or they got wrapped around the tool or blah blah blah. Why should we not do that? Why ground that tool?
Yeah, because you see in the middle of that thing, when those bars come down to start to squeeze it off, there is pressure there. That's a high static charge. And people think that plastic is an infinite electrical insulator. In other words, it doesn't matter what the charge is, it won't pass through it. Not true. It's just like anything else, there's physical limitations. Polyethylene has a fixed rate of insulating ability, okay? And for the record, for medium density PE, it's 510 volts per thousandths of an inch of thickness, okay? So if you go to 520 volts per thousand inch in that area, it's going to punch through that pipe. It's going to
really not very much.
It'll overcome it.
No.
It's really low. I mean, seriously, that's really not very much dielectric strength at all.
Well, what happens is, give you an idea, like on a half-inch service line, based on, I forget what the nominal thickness is, but I've calculated it out. It'll withstand about 45,000 volts, okay, in a service line. But I've got customers where they've got pinhole leaks in service lines going into the houses everywhere.
Yeah.
And that means that the voltage got to 45,000. And the thicker the wall, the higher the voltage it takes to arc through it. But when you squeeze that pipe and put that pressure on there and that static gets so high that if that static can find a way to ground, if that guy has not put a grounding strap on it, that electricity is going to go from that squeeze off tool through him down the ground at about 400,000 volts. Or if he puts if he puts his grounding strap on, then that charge, if it happens to arc through those pipe wall to the squeeze off rollers, it's going to go to ground and not to him. But it's important to understand that still doesn't solve your static problem on the outside of the pipe. Remember, electricity doesn't move on the outside of the pipe. It's static. So this tool grounding is strictly a worker protection measure. It has nothing to do with getting rid of static. It's not a static suppression procedure. It doesn't take the place of spraying the pipe.
I got a question now. I'm jumping ahead to the next slide. But you mentioned it before, and it's a shock due to cutting into pipe hotspots. Now, I assume that in pipelines, there's going to be certain areas that are going to have higher static charge than others, right, on a piece of pipe.
Yeah.
Is there any way to identify that?
I'll tell you a story, true story. Midwest distributor told me this story. They had an 8-inch line going into an area and a 6-inch stub coming off it. And apparently the service area had grown, so they wanted to extend the 6-inch stub. So they shut down take the line off pressure. They send a crew out there, 2 guys to go cut through this stub so they can extend the line. These 2 guys, their saw goes through, penetrates the wall, bang! Both of these guys thrown out of the excavation, off to the emergency room they go. So the gas utility was really embarrassed because they hadn't called for a locate. So they called the electric company up, the local electric company, said, "Hey, sorry, we didn't call for a locate. We struck one of your electric lines out there." And they said, "We don't have any electric lines out there." Now, that was a stub line, dead end line. How bad could it be?
Right.
It's really difficult. Now, we sell a little meter. See, your problem with static is you can't see it, smell it, hear it, taste it, feel it. You need something that has the sensory capacity to read it. Are you with me, Ted? Are you still sleeping or are you awake there now?
Well, I thought it was just a picture of him now like this.
He's holding still like this. I think his eyes are open. I'm not sure.
I'm trying not to do too much talking because my internet keeps going in and out again.
I think he's the thinking man.
But we've got a meter. We've got a meter that when you put it near a static charge, it senses the electrical field thrown off. The problem is really, given the research at GRI, you need to presume that it's there. You need to presume static's there. There are meters to read it. We sell it, but if the guy doesn't use the meter correctly, he looks at it and says 0, and there's really static there. Oops.
Yeah, you got to err on the side of caution, I guess, no matter what.
And the same thing when you got a purge line, you're going to have all this gas flowing out, so the static charges get real high. You need to dissipate the static charges to prevent both an ignition and a shock.
And then pinhole leaks. I know that's a big one.
It is going to be. I'll tell you what, people don't think this is a problem, but 5 years ago, PHMSA changed the rule on how pipe manufacturers could make polyethylene pipe, and they changed the rule specifically to limit pinhole leaks. So this is more of a problem, and guys want to sweep this under the carpet. When we talk about the Pipes Act in about another 5 or 6 slides, you're going to realize you cannot do that anymore. And what basically happens is this. Remember we talked about squeeze off and how the static charge gets so high? Yep. Or when you have a standard operation, let's say you got an operation where you're doing an operation in the field and you're doing some repairs in an excavation. Okay, well you dissipate that static before you get near it in order you don't have an ignition. But what happens if you have a piece of buried pipe and that static is built up inside that buried pipe and it's gotten higher and higher? And remember, Mother Nature wants to go to electrical neutrality. Well, what happens? That static charge arcs through the pipe wall to ground to the ground. And when it does that, the heat is so high that it melts the plastic and creates a pinhole leak. And it starts leaking microscopic, minuscule, small amounts of gas. But the problem is, generally, they don't last. They're not just one. There's more than one. This was the first paper ever written about static electricity in polypipe by a guy now He was retired from Questar, but he noticed it squeeze off. During squeeze off, after they did the squeeze off, they were getting pinhole leaks. Remember, all downstream, all the static gets so high. Well, what happens is it arcs through the pipe wall to neutralize itself. So you should always, we didn't cover this, but real quickly, whenever you do squeeze off when you're finished and you mark the pipe and you're getting ready to backfill it, before you do that, soap it for leaks, because it's very possible you've created pinhole leak.
That's a good suggestion.
Yeah.
This
so
is a cool
the pipe after squeeze off. So anyway, what happens is, this was the first paper that was ever written on, and that's what it looks like. If you had Ted Pete's Superman eyes and look into a polyethylene pipe with a pinhole leak, that's what it looks like. It looks like a lightning bolt that's going through the wall, and that's really what it is. It's a lightning bolt of static electricity. It's going through the inside of the pipe to the outside, and it filigrees and creates a leak.
That's pretty wild.
Looks like pain.
And how do you get rid of that?
Well, what a lead-in. Thanks.
Wow. And here we are.
What we originally came out with our internal static suppression cartridge to put in systems to dissipate the static primarily for safety reasons. But what's happening is if static is the cause of ignitions and it's also the cause of pinholes, well, it follows if you suppress the static inside the system, you're going to get rid of pinholes. And so we had customers who were having pinhole problems in their service lines. So we put this in and pinholes went away. We had like a 90% reduction in customers who have pinhole leaks. They've seen a 90% reduction in historical leaks when they put internal static suppression, proving GRI's research that static inside polypipe causes holes. Now, it's not 100% because there's a few leaks that are not static. They're failures, welding failures, stress, stuff like that. But it's been quite good at eliminating that. And finally, I'm going to tell you a story. Just
talked about this in the beginning.
yeah, real quick, because we've got to go on to pipes, because I think the pipes thing is the most important thing you do. Is what's going to happen is all that static that's building up. You got to be very careful. If you got areas where you're getting all of a sudden your solid state electronics is getting burned out and you don't know what's going on, it's probably not lightning. If you go to the weather websites, you'll find there was no lightning strikes in your area. The static buildup inside this pipe is going to arc through and burn out this electronics. In Kansas, they had a situation. They were doing a repair. They put the tracer wire on the pipe. They located the pipe. They squeezed the pipe off, and all of a sudden, they had not taken the clamps off the tracer wire transmitter cable. All of a sudden, the transmitter, the locating transmitter burns up. What had happened, the static charge from the squeeze off went to the tool, went to the tracer wire, and all the way back to the transmitter and burned it up. So you're going to find more and more of this, that static electricity is going to get rid of your electronics.
Is that mainly because, not mainly because, but do you see it becoming more prevalent because of everything's not analog now, everything's digital?
That's right.
I think there's more of an issue because of technology.
Yes, because all that digital stuff uses very low voltages, 2, 3, 4, 5, 6 volts. And remember, I told you service lines, you have a service line coming up to an isolation joint at a service digital service meter. That pipe underneath there could have 45,000 volts on it.
Right.
If that isolation volt, if for some reason there's a little leak, water,
It's going to melt.
It's melted, it's gone. So if you notice burnout of electronics, don't assume it's a lightning. It's probably static electricity in the pipe.
Here's a slide that I don't know what it means.
This is Statute 2299 of the United States Code. This is going to affect our natural gas industry more than anything I think that's happened in the last 20 years. And essentially, it's the Pipes Act. And what happened was, they had that overpressure incident in Massachusetts.
Correct.
So what they did is they passed this act, the Pipes Act. And essentially, most of the act deals with trying to prevent overpressurization again. However, they put this in it. Up until this time, gas companies were not required to take into account methane emissions in the operation of their systems. PHMSA is now legally empowered to take into account methane emissions in their rulemaking, in their cost analysis. Okay? So that means that what can happen then is that means that PHMSA has the ability to regulate your emissions. They have the legal mandate to do it. And they can sit there and say, listen, the cost of the climate with your methane emissions are such and require you to go do this. Now, several states like Massachusetts, they're already requiring LDC, local gas companies, and this applies to all methane, the whole methane chain, but it applies to LDCs. Massachusetts, for instance, LDCs are required to show diminishing amounts of methane emissions every year. So in their rulemaking, let's say you had a leak, like a pinhole leak, okay? That's a grade 3 leak, not a safety issue. 50 months, 2 years.
Not anymore.
Not now. You've got to get that taken care of now.
What's the time frame on it? Have they established a time frame? Like, is it?
No. What happened? Let me tell you the background. They had their first public meeting on leak detection, methane emissions, and repair for gas pipelines back in May. And two of the presenters, if you want to know where this is going, okay, two of the presenters. The first presenter was the EPA. EPA right now does not have jurisdiction with gas companies on methane emissions. Only PHMSA does. But they were in there to say, we want reduction in methane emissions.
Sure.
The Environmental Defense Fund gave a presentation. They are going to be watching LDCs to prevent emissions. So they're going through the rulemaking process right now. But the point being is, this is going to get, gas companies treated leaks as a safety issue. That's right. Not the case anymore. It is primarily, you are primarily now a polluter, and you got to also make sure it's a safe pollution.
Safety and a pollution issue. Which brings us to the next slide. Wait a minute. What LDCs can expect in methane emissions?
Yeah, what happened is the Senate has already approved reinstating methane emissions control on gas producers, and they're working right down the chain. They have done studies. That show that LDCs are leaking a lot more gas than they did. Now, see what happened? There was no financial. If it wasn't a safety issue, and because it's part of lost and unaccounted for gas, there was no cost out of pocket.
Right.
What difference does it make? All that lost and accounting for gas, they want that gone. They want that accounted for. You can't just say, "Oh, it's a meter reading problem."
Right.
They're going to want it. They're going to say, if you can't account for it, you got a leak you just haven't found. That's
which means a lot of things are going to be changing, I guess, right?
People have very serious. You're not only going to have you've been dealing with safety pipeline guys, but you're going to deal with PHMSA on methane emissions. I don't think there's any question. In 4 years, the EPA is going to get jurisdiction jurisdiction to enforce methane emissions leak, and they operate on an entirely different basis. Do you have 1 second? How are we doing the time, Joe?
All right.
There was an oil right now.
I'm still interested, so keep talking.
Yeah,
oil and gas guys Trump tried to remove the methane emissions from it, but it was put back on. But there was an ongoing suit that had a consent decree done, and it just came out like January this year. And this will give you an idea of how enforcement with the EPA will be as opposed to your pipeline safety guy. It was about a $40 million a year oil and gas company. They were out in Denver, Colorado. They were having VOC emissions and methane emissions from their system. And in the Denver area, that atmosphere is compromised. So they have more strict standards of pollution control because it's an area designated. The air is not as clean as it should be. They finally all agreed. EPA came after them. They finally all agreed. So that $40 million company agreed to a $1 million civil penalty. Two, they had to do $2.5 million of remediation. So basically, for the $2.5 million of improved equipment and everything they put a 30% penalty on there to encourage people not to let this happen again.
Right.
Now, that was a $40 million company. Now, there's a lot of smaller gas companies that are $40 million in revenue. Yeah. And you all of a sudden get the EPA coming after and throwing you $1 million fine. That was the negotiated one. That's what they finally agreed on, not what they proposed.
That's crazy.
So this is what's coming down the road. So you companies, you got to start getting these leaks under control. We take care of the pinhole problem.
Wouldn't you want to take that $1 million fine and put it back into making the pipelines better?
Right.
Well, what they did is EPA, that goes toward part of the enforcement costs. And then in Colorado, they have an air quality board, and they split the fine with the air quality board.
That's what I mean, though. Like, it's not done for the right reason. It's not done to actually
The government takes the money. Why don't they take $1 million and put it back into what's wrong?
That's what's. Anyways,
well, what happened is that what they did is the oil and gas company had to put the $2.5 million in. But you know, this is a deterrent. This is designed to send a message out there saying.
So then the oil and gas company then raise their rates on the consumer to be able to bridge the gap.
I don't know how they did it.
That's what I mean, though. There's that trickle down. It ends up out of everybody's pocket somehow.
Let me tell you what the EPA does. See, in the gas industry, you look at a leak and say, I got a leak here, okay? And then I got a leak down here, okay? And you look at them and say, oop, that's a safety issue. Oop, that's not.
Right.
Now, those leaks may be 500 feet apart, okay? EPA does not see it as – they see it as pollution. They see it as a, quote, source. So what happens is they come in and let's say, like I've got customers who've had pinhole leaks in areas of their service lines. Well, they say, oh, I got 18 leaks here. That's not what the EPA says. They go and look at that whole area. They count up all the leaks, and if the total emissions – reaches a certain threshold, it is now a source, and you need a permit for it.
Wow.
That's what they do in the oil and gas. Now, I purposely asked the EPA guy a question. I said, are you going to treat the definition of a source the same in LDCs as you do oil and gas? And I can't repeat the answer because I didn't really quite get a clear answer of what it was.
I don't think they know yet. Well, with all that being said, let's dial back to let's get back to the static part of it. Yeah. I really appreciate the information. I think a lot of people would appreciate watching that and understanding.
No, please, I cannot emphasize enough. This is coming down the line. All leaks, fix your gaskets, your compressors. Start now. Do not wait. This is coming fast down the line, and we can prevent pinhole leaks. If you put our static suppression cartridge where you're experiencing pinhole leaks, it's gotten rid of 90% of them. So it's a lot easier to prevent leaks than to locate them, dig them up, and repair them.
And I'm just going to bring the last slide up so everybody can, if they need to get in contact with you or they have any more questions, it's on there. You can also reach out to any of us for Dirk's information if you don't catch it right now. Dirk, I just want to say thanks, man. Like, I always love your presentations because I love your passion for what you do. I think it's really cool that, you know, most people don't know this, that Mr. Dirk here, let me just turn that off. Mr. Dirk here, originally, I believe, started working and figured out static when you worked in the printing press, correct?
Yeah, the processes we developed in the printing industry, we put them in. Our static eliminators, if you got a $20 bill in your pocket, our static eliminators treat every $20 bill printed in the United States. They do.
That's great. I love that.
Treat them all the same, right?
Yeah.
Yeah, look at you.
It's all kinds of, we could have a lot of different applications.
And randomly, Dirk, you can also manage your own static for $20 or so.
Yeah, look at that. Yeah.
The only thing it doesn't, our static process works on everything except wives and girlfriends. So you're on your own.
Well, I'm out.
Please, if you're an LDC, listen, start now, get proactive in these leaks. It is not going to be pretty. There's people out there that are going to hammer us on methane emissions, and they're going to want it done fast. And we
don't do much fast.
Yeah.
All right. Well, we're going to let everybody go because we've been chatting for.
Yeah, we've been going at it for a while. So it's great being with you guys. And hey, listen, we're having quit using. We're having suntan lotion is getting rationed down here at Boca Raton. So if you would guys kind of ease up on it, so you can spare.
Sure, they're down there in Boca.
Fly down here for us.
If this wasn't live, I'd probably show you something. But
well, I'm glad we'll keep it on a very professional basis. It's always great being with Manny, Mo, and Jack of the Natural.
There you go.
Have
Dirk,
a great
thanks, Dirk.
Thanks for having me.
Dirk, thank you. Thank our viewers for watching this. We truly appreciate you guys. We'll talk to you later and soon.
Take care. Bye.